Hello, this is Exam 1 from Spring 2016 for Calc 3. I have been putting this one off for a while, not because it's a hard exam, but because I am just lazy like that. So, let's get going. Question number 1. The two values of x for which these two vectors are perpendicular are what? So we know that two vectors are perpendicular if their dot products are 0, so let's set that up. X squared actually, sorry, I need to change my pen setting. I hate this one. There we go. That's better. X squared times 1 minus 5x plus 6. We know that has to be equal to 0. And all I'm doing here, we know for the dot product, we're just multiplying each of these individual components together and adding the result. We want this to be equal to 0. Well, we can simplify this down a little bit, and this whole thing is going to factor to x minus 3, x minus 2 is equal to 0. And so that gives us two values, x equals 2 and x equals 3. Question number 2. The plane passing through the point 0, 1, 0 is parallel to that plane, and we're looking for the point where our first plane, the one that we have to find, intersects the x-axis. So, since our plane is parallel to this plane here, we know that they have to have the same normal vector. So we know that the left-hand side of our plane equation is going to be x plus y minus 2z, and that's just going to be equal to some other constant. And really, you can just think about this as we have two planes that have the same slope in 3 dimensions, but they're just offset from each other by some amount. So we see that we pass through the point 0, 1, 0, so when we plug this in, we see that this must be equal to 1, plugging in 0 for x, 1 for y, 0 for z, and we're looking for where this intersects the x-axis. Well, we intersect the x-axis when x and y are both equal to 0. So when I said x and y, I meant y and z, so we're going to be left with x equals 1, and so our point is 1, 0, 0. Okay, an arc length question. We know that the formula for this is just going to be the integral from -1 to 1, so we're integrating over our bounds on t dt, and inside this integral we're going to have the magnitude, I always do that, of r prime of t, like that. In the last video I made the mistake of saying the magnitude, but then I wrote a square root. It is not the square root of r of t, it's the square root of the square of all the components of r of t added together. You know how we do, how we compute the magnitude. So in order to find this guy right here, we're going to need our r prime of t, which will just be the individual components of r of t dt. So we'll get 3t squared root 6t and 1. And the magnitude of this is going to be the square root of 9t to the 4th plus 6t squared plus 1. This is going to factor to the square root of 3t squared plus 1 squared. These guys are going to cancel, and we will be left with the integral from -1 to 1 of 3t squared plus 1. This integral will evaluate to t cubed plus t on -1 to 1, which will give us, oh, you didn't see that, which will give us 4. Don't worry about it. Okay, question 4, we have a limit here right off the bat. This is looking like it's not going to exist, but we have to prove it to ourselves. Why do I think it doesn't exist? Well, if we take a look at it, there's no single term that we can factor out to cancel something out. And also when we plug in 0, 0, we do get 0 over 0. So that's not a very good sign for us. So with the hunch that it doesn't exist, let's apply the two-path test. Let's approach this limit on the line x equals 0. So for every x in this limit, let's replace it with 0, and we get 0 over 0 plus y squared. When we apply this limit to this guy, we're still going to get, excuse me, 0 over 0, which is no good. But it's actually good for us because we're halfway there to proving that it doesn't exist. And secondly, let's approach it on the line x equals y. So for every x, we will replace it with a y. That would give us y cubed over y to the fourth plus y squared, which is the same thing as y over y squared plus 1. And this is important because when we plug in x equals 0, y equals 0, we're not going to get 0 over 0. We're going to get 0 over 1, which is real 0. Nothing like this fake 0 we got going on over here. So because we have found two different results, there can be no single value that this limit approaches for every single possible path in 3D space, so this limit don't exist. Let's find the equation of the line that passes through that point that's parallel to the vector tangent to this curve at that point. Okay, so there are a lot of adjectives going on in this question that make it a little difficult to unpack. But let's see what we can do. So we know that we want to be parallel to the vector tangent to this curve. So when I hear tangent to r of t, I think r prime of t. So let's find that r prime of t to start off with. 2t plus 3. Oh no, we have a whole big thing here, don't we? E to the t cosine t minus e to the t sine t 1 over t plus 1. Okay, so it's a little yuckier than we would want it to be, but that's fine. So now we'll also notice that we're looking at the point 2, 1, 0. Well, in order for this r of t to go through 2, 1, 0, our t value has to be 0 because, you know, ln of 1 is 0. Let's see, e to the t cosine t, that needs to be 0. And over here, we just want that constant 2. So all these other t's have to be 0. So all we get from that is that we need to be evaluating our r of t at 0. So r prime of 0 is going to be 3. And then, let's see, 1 minus 0, and then 1. Okay, awesome. So we are actually in the home stretch. We have all the numbers we need here. So we know that we want to be parallel to this guy. So our parametrization in terms of x, y, and z, these are going to be the slopes in order to stay parallel the whole way through. And we also know that we have to pass through the point 1, 2, 1. So our parametrization is going to be x equals 3t plus 1, y equals t plus 2, z equals t plus 1. And let's see where that is. That's answer choice A. Perfect. 6. A particle starts at the origin with that initial velocity, and we're given its acceleration. Find its position. You cannot get a particle motion question that's more standard than this. This is about as normal as they can possibly make it, which is nice because we know exactly how to do this. We have to take the integral of each of these components. We're starting with a of t, integrate each of these components, and adjust for our initial velocities and initial positions. But first, let's translate this into numbers. We see that we have this little sentence fragment here. A particle starts at the origin. Well, I guess that would be a full sentence. I don't really care. What that translates to is that r of, well, it doesn't have to be 0. Yes, it does. R of 0 is 0, 0, 0. And that'll be important in a second. So let's integrate the integral of a of t dt, all these components, is going to be t squared over 2. And then for v of 0, we want to get 1, negative 1, 0. And so we're going to have to add a 1 here to satisfy that condition. For our second term, t squared over 2 minus 1, we're going to have to add a constant of negative 1 over there. And for our final term, we're going to get t. And we don't have to do anything to that, because when we plug in 0 for that value, that matches our v0 that we have up there. Okay, so this is equal to v of t. And for our final, well, our second to last step, we're taking the integral of v of t dt and doing the exact same process. T cubed over 6 plus t, and then we want to be at the origin, so no constants needed here, because plug in 0 for t, and this component is going to be 0. Again, t cubed over 6 minus t, we don't need to do anything. T squared over 2, we don't need to do anything. And finally, our final step, because this is r of t, we need to find r of 1, which will be 7/6, 5/6, and 1/2. Sorry, and by 5/6 I do mean negative 5/6. We will have a negative 1 there. So D is our answer for question 6. Let's use let's use the linear approximation, this guy, at the point 4, 3, to approximate the value of this thing. So this is pretty scary, but all we have to recognize is our linear approximation, and I like to kind of make stuff up for this. Don't worry, it still works. We're going to call our linear approximation L. This is just going to be, fx dx plus fy dy. And what does that mean? Well, that's just the partial derivative of f with respect to x, evaluated at 4, 3, multiplied by dx, which is just going to be the change in our x value. And we can actually go and find dx and dy right off the bat, because we know we're starting at the point 4, 3. We're approximating the point 4.02, 2.97. So dx is going to be positive 0.02, and dy is going to be negative 0.03, like that. And I would plug those in. This becomes a pretty yucky problem to do the computations on in just a little bit. But before we get to any of that nonsense, we have to find our fx. So the partial derivative of this guy with respect to x is going to be x over root x squared plus 3y. And fy will be 3 over 2 root x squared plus 3y. And we have to evaluate these guys at 4, 3, because that's still the point that we care about. So all of these square roots are going to turn into 5, because we're going to get 16 x squared plus 9, which is 3y. That will give us 25. So we can say that this is going to be equal to 4 over 5. Excuse me. And this guy right here will be 3 over 10. Okay, so we are just about ready to plug these guys in. So, sorry, I'll rewrite everything down here. Our linear, Okay, sorry, I should have been more clear. This is not going to be the linear approximation. This, I'm really sorry, that was misleading. This is the total, I'll call it, I don't know, I'll call it delta f. The total change in our function is going to be given by this guy. And we're going to have to, do some more evaluation at the end. It'll all come together. It's a little bit of a process. But in the meantime, let's do fx dx, which is going to be 4 over 5 times 0.02, and we're going to add to that 3 over 10 times negative 0.03. Okay, let's put everything into decimal. 0.3 and 0.8. This is going to give us 0.016, and this will give us 0.009. There we go. And so overall, we get positive 0.007. Okay, so like I said, I kind of figured it out in my mistake in the middle there. Like you saw, this is our total change in our function f. So now we need to know what our function is anyway. Well, our function is just going to be f of x when we plug in 4 and 3. And we saw earlier, and you can do it now, that's going to give us 5. And so in the end, our answer is 5.007. 7 is E. Okay, I'm sorry, that was a little bit, I hope that was more painful for me than it was for you, but I hope the message got across in the end. Yeah, sorry about that. This is, I almost saw this using differentials. This is really a differential expression here, but it works perfectly fine. Your other option, which is more direct, is effectively setting up a tangent plane equation and solving it like that. That would also work. Okay, here we go. We have a multivariable chain rule question. We're looking for dz dt, where z is composed of x and y, x is composed of t, and y is also equal to a function of t, which is they're calling h. I hate when they add that extra kind of step in, but we can deal with it. So we know that by the multivariable chain rule, dz dt is going to be zx xt plus zy yt. And these blanks are very easy to fill in this case. Let's find zx and zy. That will just be y cosine xy and x cosine xy. Okay, we can also find xt and yt relatively easily, since we know that y is equal to h of t, and that h prime at t equals 1, which is the value of t that we care about, is 2, yt is also 2. Then for xt, it's just the partial derivative of x with respect to t, which is x equals 2 pi t. For t is equal to 1, x is equal to 2 pi. There we go. And now we can plug our values for x into, sorry. This is, I should be more clear. This is xt up here. We took a partial derivative. So the other thing we do need to figure out is what are our values for x and y? Well, we just have to plug in t equals 1 up here. So x is equal to pi, and y, since y is equal to h of t, and that h of 1 is 1/3, y is equal to 1/3. So now we can start solving these guys over here. So this expression right here, we are going to get 1/3 times the cosine of pi over 3, which will give us 1/6. And then here we are going to get pi over 2. And then finally, multiplying these guys and adding the results, we will get pi over 3 plus pi or 4 pi over 3. Question 9, the directional derivative of this guy at this point in this direction is what? So they tell you to use a directional derivative here, but often they will not, and you'll just have to know to look for these three kind of unique identifiers of a directional derivative where you're given a function at a point in some direction, and you're asked to find some sort of rate of change. Okay, but we know how to do this. All this is going to be is the gradient vector, fx, fy, fz, dotted with the, here we go, the unit vector of the direction that we are pointing in. So let's figure these guys out. fx, fy, fz, we can all solve for relatively easily. We will get y squared e to the x minus z. Nothing's changing there. 2y e to the x minus z, and negative y squared e to the x minus z. And we can go ahead and evaluate these guys at our point, which is 3, 1, 2. And we are going to get e, 2e, and negative e. Awesome. So we already know half of our big dot product. I'll give myself some more space down here. E, 2e, not negative 3, negative e. Those are our values for our partial derivatives. We know that the direction that we're pointing in is given by this vector here. Let's see, I'll write this out. 2, 5, 1, and we need to find the magnitude of that. Well, that's just going to be 25 plus 4 plus 1, so 30. So we need to divide everything by root 30, and we have our unit vector. So let's bring that. In fact, I can watch this. I can grab it and move it. I should do that more often in these videos. So we are all ready to solve. We're just going to get 2e plus 10e minus e, so 11e over root 30. Like so. D for question 9. There we go. Question 10, let's reverse the order of integration and compute this guy right here. So it's always, oh wait, sorry, I forgot. This is not this is not on your exam. You learn this later. You'll learn this like a week and a half after your exam. But I don't know. If you want to stick around, feel free. But I don't know. I definitely won't blame you if you go look at something else. But I could use the practice. So let's do it. Let's reverse the order of integration. So we have a double rectangular integral here, where our lower bound on y is the line y equals x, and our upper bound is the line y equals 2. We also see that x runs from 0 to 2, and we are looking, at this region right in here. So to reverse our order of integration, we know that we want to kind of draw arrows, and since we want to integrate dx first, let's set this up. Integral dx dy, we see that our arrow parallel to the x-axis enters our region in the line x equals 0 and leaves it at the line x equals y. And then for y, we just want our extreme values, which are 0 and 2. This is actually a really good intro question for this topic. A lot of them deal with much weirder functions in this, but so if you're sticking around, good on you. Maybe this will be good practice for you in the end. And then our integrand is just going to stay the same. I hope I did explain it well. I probably didn't. I haven't done this in months, so I hope you'll forgive me. So our first integration, we have no x's, so this whole thing is just going to lead to a y getting multiplied in. And now we're left with something that we can integrate by parts. And if this is your first, I really hope this isn't anyone's first introduction to this. This is a lot of pressure for me. But the reason that we can't integrate this directly is because we will get to a state where we cannot do integration by parts. We'll be left with a really lonely, part of the expression that will be very, very difficult to integrate by the methods that we know. In fact, impossible, given like Calc 2 integration. So we have to do something like this, but now we're left with something that we can deal with pretty easily. We'll set u equal to 2y du, sorry, by 2y I mean y squared. Du will be 2y dy, and then our bounds on integration are going to change from 0 to 2 to 0 to 4, and then this will become e to the u over 2 du. Integrating, we will get, you guessed it, e to the u over 2 evaluated on 0 to 4. So e to the 4 over 2 minus 1, because here we're just going to get a 1. So that is our answer there. Oh, sorry, we don't get a 1 here. We get a 1 over 2. We still have that 1/2. So our answer is answer choice A for question 10. Let's see, question 11 has minimums and maximums and saddle points, and we have to figure out, the distribution of each. This is a really good function for this. I don't know, they've used this exact one multiple times if I remember correctly, so it's a good one to get used to. But we know, and this is just about like the 40th time I think I've done this little explanation, so hopefully it's better than it used to be. Maybe, I don't know. We know for these second derivative test questions that this is one of, we are going to end up with a matrix. This matrix is going to have fxx, fxy, fyx, and fyy in it. And there are some rules about this matrix. If the determinant is greater than 0, then we have two choices. If fxx is less than 0, we have a local max. If fxx is greater than 0, we have a min. If the discriminant is less than 0, we have a saddle. And if the discriminant is equal to 0, and I always draw, I'm not sure why, I always draw a sad face here because it kind of is sad. We don't know anything. Those are our rules. Whatever you need to do, drill them into your brain. Do not forget them. They're your friend, So let's figure these guys out. And we should also note that the only candidate points to be local minimums and maximums are points where fx and fy are both equal to 0. So that's what we're looking for here. So, but in order to find fxx and fxy, we first have to find our first order partial derivatives. This is just going to be 6x squared plus 6y and 6y plus 6x. Did I do that right? Yes, I did. Okay, we're good. So where are these two equal to 0? Well, they're equal to 0 when we're at the point 0, 0. Hopefully that's one that no one's going to miss. Let's see. At the point 1, negative 1, both of these are equal to 0. And you can check these for yourself. I'm kind of just doing it in my head. 1, negative 1. Yep. Let's see. And that is it. And you can always check if that's it by seeing if all of the if all the answer choices reference a certain number of critical points. In this case, every answer choice talks about two different ones. Sometimes they'll try to be a little sneakier and reference different numbers of critical points, but in here we are good, and these are the only two critical points we have to care about. So let's make our matrix here. Fxx is going to be 12x, fxy and fyx are both going to be 6, and so is fyy. When we plug 0, 0 into this matrix, we are going to get a negative determinant. Remember that the determinant is AD minus BC, where the positions in our matrix are A, B, C, D, like that. I already said that, right? AD minus BC. Okay, we're good. So we know that this is going to be a saddle point, and we can just take a look over here. That was our rule. If the determinant is less than 0, we're dealing with a saddle point. And finally, for this guy right here, if we plug in 1 for x, we are going to get a positive determinant with a positive fxx, so that will be a local minimum. And so our answer for 11 is C. Number 12, let's find the absolute maximum and minimum values of that function on this ellipse. And we, yet again, have to be very happy that this is an equal sign and not a less than or equal to sign. Because if it was, it would mean that we would have to do the whole second derivative test to search the inside of our ellipse for other critical points, whereas all we have to do is search the outside. So interestingly enough, really it's not interesting, it's kind of bad. I have forgotten the method that they taught you guys. By you guys, I also mean me, I took it last semester, that they taught for this kind of question before we learn Lagrange multipliers, because right after your exam, they teach you a much better way of doing this, and I'm going to do that much better way right now. So, but it's really not that bad, and I think you can pick it up in a couple questions. And if this makes absolutely no sense, you can always go check out the whole video I have on Lagrange multipliers, if that's the kind of thing you want to, do with your time. So, with Lagrange multipliers, we need to identify two things. We need to identify the function that we're trying to maximize or minimize, and we also need to identify the function that is constraining our first function. So in this case, since we're bound only to the boundary of this ellipse here, the ellipse is our constraint function, and we call that, well, it's g of xy. That's our function g, just our constraint. And then the function that we're maximizing or minimizing, well, we just call that f of xy. Okay, so what are we setting up for this? Well, we're going to set up fx equals gx times some constant lambda. And I'm never sure if I'm actually drawing my lambdas backwards, or if I'm drawing them the right way or the wrong way. Someone should let me know. And then fy equals gy lambda. And all this lambda is a constant that allows us to set these guys equal to each other. You'll kind of see how it goes. So fx, we're going to compute that as just 2x. Fy is 2y plus 2. Gx is 2x. And, gy is 4y. Okay, so let's plug all these guys in. We see that 2x is equal to 2x lambda. We also see that 2y plus 2 is equal to 4y lambda. And this is a very easy Lagrange multiplier question, because if we divide 2y out of our first one, we see that lambda is equal to 1. And when lambda is equal to 1, things get easy, because if lambda is 1, then this guy right here is going to simplify down to 2y plus 2 equals 4y, or just 2y equals 2, which is the same thing as y equals 1. And whenever we get to this point where we've actually learned something about one of the values of one of our functions, we always go back up and plug that into our constraint function. Oh, well, you can tell that I did a cut because we already computed it. Sorry, I forgot to delete that. So when we plug in y equals 1, we will see that we get x squared equals 6, or x is equal to plus or minus root 6. And you might think, okay, well, now we have our two critical points. One of these should be a maximum, one should be a minimum. We're probably done. But that's actually not true, because any value that we take for x is just going to get squared up in here. And so that doesn't matter. So there is some other critical point that we're missing. And it's actually baked into one of the assumptions that we made over here, which is that lambda has to be equal to 1. If lambda is not 1, then the only other way that this expression can be true is if x is equal to 0. And if x is equal to 0, well, we can go back up to our constraint function to figure out what y is going to be. Well, if x is equal to 0, then 2y squared is equal to 8, or just y is equal to plus or minus 2. There we go. So now we have 4 different critical points that all could be maximums or minimums, and we have to go plug these into our function f of x up here. So writing out our critical points, we have 0, 2, 0, negative 2, and 1 comma, sorry, got that wrong, root 6 comma 1. And we already said that negative root 6 comma 1 will give us exactly the same answer. So we can leave that out for now. So going from the bottom, plugging in root 6 comma 1 in to our f of x up here to see if it's a max or a minimum, we are going to get root 6 squared, so 6 plus 1 plus 2, which is 9. And since a lot of these maxes are listed as 9, it's a pretty good indication that B, D, or E could be our correct answer. So it's all kind of riding on the minimums here. So let's try 0 comma 2. Well, 0 comma 2 is just going to give us 0 plus 4 plus 4, which is 8, which is less than 9, so that definitely can't be our max, but it's also not our min. So this point is really useless to us, but let's try 0, negative 2. That's going to give us 0 plus 4 minus 4, which is 0. And our answer, thank God, is B, and we are done. Sorry, this was a little bit of a sloppy exam for me, or at least it felt like it when I was recording it. Hopefully I clean it up a little bit in editing, but I hope this was vaguely informative. And I don't actually know how many people, watch these through to the end or end up listening to my weird little rants. But, thanks, I guess. See ya.